What's up, everybody? It's Dan from SageMathTutoring.com, and I'm here with another video, this time a video about prime factorization, converting fractional exponents into radicals, and then simplifying radicals as well. So let's get right to it. Prime factorization. Well, first of all, what are prime numbers? Prime numbers are those numbers that are divisible only by themselves and 1. And interestingly, the first prime number is 2. The next one on the list is 3. The next one on the list is 5. Then it goes to 7. It wouldn't be 9. One might be tempted to think that it's 9, but remember, 9 is not only divisible by itself in 1, but 9 is also divisible by 3. So therefore, 9 is not a prime number. The next prime number in the list, however, would be 11. Then we have 13, not 15, 17, 19, not 21, but 23. Now you might notice that all of these are odd, right, except for this one. And it is the case that 2 is the only non-odd prime number, also known as even, okay? Now the reality is that there's infinite prime numbers, which is something that mathematicians have proven, which is pretty fascinating, actually. So it's the case that these would go on forever, okay? But I think to go up from 2 to 23 is enough to serve our purposes at this point. So you might be wondering, why am I listing the prime numbers? Well, once again, we're going to be doing prime factorization, and prime factorization means, like, if you take a number like, I don't know, let's say 150. And let's say we wanted to do a prime factorization on 150. Well, the way that I like to go about things is methodically. So I would always start at the top of the list. Okay, I would actually write this list, up to around 23, maybe 19, maybe 17, I don't know. But I would start at the top of the list. And then I would ask myself, does 2 go into this number? If the answer is yes, then you can do these 2 little branches. And one of the branches is going to get the 2. And the other branch is going to get the factor, the other factor. So it would be 2 times 75 in that case, right? 2 times 75. Now, since this is already prime, we can just kind of leave that one alone. We're going to shift our focus to this, and we go to the top of the list. We go to 2 again. We ask ourselves, does 2 go into 75? Well, the answer is no. So therefore, we go to the next one on the list. Does 3 go into 75? Well, yes, it does. So then we can do these 2 little branches. You put a 3 over here, and then the other factor happens to be 25. 3 times 25 gives you 75. So that's prime. So we leave it alone. We focus our attention on this number, and we go to the top of the list. We go to 2. We ask ourselves, does 2 go into 25? The answer is no. Does 3 go into 25? No. So then we go to the next one on the list. Does 5 go into 25? Well, yes, it does. So therefore, we would have 5 times 5. And once you have all prime numbers at the tips of these branches here, then you're actually done. Okay, so we have a prime number here, we have a prime number here, and we have a prime number here. Now, one of the skills that, in my opinion, is very important is rewriting 150 only in that sort of prime factorization form. So you're going to have 150. By the way, that equals, and all you have to do is take note of who are the characters in the cast of characters. We have 2, we have 3, and we have 5, right? I know we have a double 5, but as far as the unique characters in the cast of characters, it's certainly 2 times 3 times 5. Now, since it's the case that we have 2 of these 5s, then we could put an exponent of 2 right there. Okay, so in other words, if we were to kind of back up a little bit, or if we were to investigate this, what I'm saying is that 150 actually equals the product of all of those prime factors that we made. So it's 2 times 3 times 5 times another 5. And you could always double check that. 2 times 3 is 6, 6 times 5 is 30, 30 times 5 is 150. Sure enough, they all multiply to 150. So that's an interesting thing that happens with prime factorization. The tips of the branches are not only prime, but it's the case that if you were to multiply all the tips of the branches, you would actually get 150. So that is a skill that's very important for the problems to follow. I feel like we're going to get plenty more examples soon. So this is the only example I'm going to offer right here. But once again, list the prime numbers, perform the prime factorization according to that methodical strategy, and then hopefully rewrite the original number only in terms of its prime factors. So another skill that's going to become important for the following worksheet is the fact that there are certain exponent laws that are important. So for example, let's say I had something like 5 squared, and yet that was raised to the third power, okay? Well, whenever you have a base or a power or an exponent being raised to yet another exponent, you actually keep the base and then you multiply the two exponents, okay? Now, that is a very sort of well-known law of exponents. Once again, anytime you have an exponent raised to another exponent, you keep the base and multiply the exponents, okay? Now, most of the time, teachers will ask students to kind of move from this position to that position. However, as is the case with certain math concepts, this is one of those concepts where it's going to be helpful to go backwards to turn something like 5 to the sixth back into 5 squared raised to the third power. Now, you're going to see a context where that's necessary, okay? But for now, all I want to just demonstrate is that if you wanted to turn 5 to the sixth into something that looks like that, you could, okay? Similarly, let's say I had something like, 7 to the fourth power. Well, that could be rewritten as 7 squared again. Okay, so if you think about it, all we're doing is we're just breaking 4 up into factors. In this case, it's 2 and 2. All right. Another example might be the fact that we could always raise 2 to the, let's see, 10th power. Well, that could be rewritten as 2 to the 5th power raised to the 2nd power, or it could be rewritten as 2 to the 2nd power raised to the 5th power. Okay. Now, once again, the context in future problems is going to make it clear which of these we need to do. But all I want to demonstrate on this particular slide is that you can do that if you want. Okay, so that's a skill, sort of turning these sort of normal bases and exponents into this sort of split version. Okay, that's going to be a skill that is helpful soon. Now, another skill that's going to be helpful soon is just the fact that if you had something like 3 to the 5th or something, you could always kind of recognize that that's really just a 3 times 3 times 3 times 3 times 3, right? It's really just 5 threes all getting multiplied together. And the reality is that you could kind of focus on just these two and these three, and therefore, if you wanted to, you don't have to, you could acknowledge that this is really just 3 squared, and this is really 3 to the third. And therefore, if you wanted to, you could represent 3 to the 5th power as 3 squared times 3 to the third. Okay, so in other words, you could sort of split the bases in that way. Now, notice that when you split the exponents, it's going to be splitting the exponent into factors of the exponent. But when you split the bases like this, then the exponents, it's more of an addition sum situation because 2 plus 3 equals 5. Okay, so hopefully that makes sense. Let's look at another example. Let's say I had 2 to the 10th power. Well, in reality, that's really just 10 twos getting multiplied together. We have 2, 2, 2, 2, 2, 2, 2, 2, 2, and 2. I think that's 10. Right? So the reality is we have a lot of options here. We could focus maybe on just these three and focus on these. So that would be 2 to the third, and this would be 2 to the seventh. And therefore, we do have the option. We have the option. That's all I want to sort of suggest. We have the option of rewriting 2 to the 10th power as 2 to the third power times 2 to the seventh, 2 to the seventh power. Now, once again, notice how if you're splitting the bases, not splitting the exponents, but if you're splitting the bases, the exponents themselves would have to add to the original exponent. Okay, so that right there is going to be an important skill to keep in mind in the future as well. And finally, a third skill that's going to be super helpful is just really understanding the concept of a multiple. Okay, now a multiple is basically when Like if you have a number like 3 or something and you want to know what's a multiple of 3. Well, first of all, every number is a multiple of itself. Okay, so we could say a multiple of 3 would be 3, right? But the next multiple of 3 would be 6, and then another multiple of 3 would be 9, and another multiple of 3 would be 12, and then it kind of goes on like that. So as a reminder, the concept of multiple, like if you have 3 and you want to know what a multiple of 3 is, what you're really asking is what are some other numbers that 3 divides into? Okay, very often larger numbers that 3 divides into. Once again, every number is a multiple of itself because 3 times 1 gives you 3. But typically, the multiples, like the list of multiples, most people would associate that with larger numbers. So we know that 6 is a multiple of 3 because 3 times 2 gives you 6. We know that 9 is a multiple of 3 because 3 times 3 gives you 9. We know that 12 is a multiple of 3 because 3 times 4 gives you 12. You know what else is a multiple of 3? Let's see, I don't know, 60. You know why? Because 3 times 20 gives you 60. In other words, 60 is divisible by 3. That's why 60 is a multiple of 3. 12 is divisible by 3. That's why 12 is a multiple of 3. 9 is divisible by 3. That's why it's a multiple of 3. 6 is divisible by 3. That's why 6 is a multiple of 3. And finally, 3 is divisible by 3. That's why 3 is a multiple of 3. So if I wanted to analyze perhaps multiples of 7, well, of course, a multiple of 7 would be 7 because every number is multiple of itself. But you know what else would be a multiple of 7? 28. You know why? Because 7 times 4 gives you 28. In other words, 28 is divisible by 7. Anyway, basic concept. I know for many of you watching, that's like perhaps unnecessary review. But for my student who might be watching this, I do believe this concept needs to be fresh on your mind. It needs to be at the top of your mind when it comes to the problems to follow. So, quick recap. Anytime you have a power raised to another power, you can keep the base and multiply the exponents, but similarly, you could also split the exponent into factors of 4 while keeping the base and rewrite it like this. You could split this 10 into factors of 10, keeping the base as is, so that would become 2 to the 5th to the 2nd. That's a possibility. Another possibility is 2 squared to the 5th. That's a possibility. When it comes to rewriting 3 to the 5th, like this is just a normal situation as well. Occasionally, it might be helpful to split the base. And anytime you split the base, you need to make sure that the exponents actually add up to the original exponent. So the first skill that I covered is prime factorization itself, but there's another skill that's going to become necessary when it comes to simplifying radicals. So for example, let's say I have the cube root of 2 times 3 squared times, let's say, 5 to the third underneath there. Okay, so this is all prime factors of some larger number. Um, so the question is, if you're uh, facing something like this, well, how do you simplify it? Well, the way that I like to go about this, it's a way I learned a long time ago. And that is to treat each of these prime factors as though they're a prisoner inside a prison. Okay, now the prison itself is this radical symbol, whereas these, I'm going to call them the bases. The prime factors, I'm going to call the bases. The bases are prisoners. Now, a prisoner does not get out of jail unless the prisoner can show the jail guard an exponent an exponent that matches this number here. We call this the index, okay? So if a prisoner is able to show the jail guard person an exponent that matches the index, that prisoner gets out of jail. So this 2 is one prisoner, and this 2 happens to be stuck in jail because the 2 does not have an exponent that matches this number, okay? Similarly, this prisoner called 3 does not have an exponent that matches this number. So therefore, 3 is stuck in jail. However, this prisoner called 5, is definitely showing an exponent that matches the index. So it is the 5 that gets out of jail, not 5 to the third, but 5 itself. So who's left over? Well, we got the 2 times 3 squared. That's who's left over. Now, 3 squared is, of course, 9, and 2 times 9 is 18. So we could sort of rewrite this as the cube root of 18, and that is as simplified as that radical can be. All right. Now, let's do another example only featuring square roots because square roots are a little bit more common. So let's say we have the square root of like 2 squared, um, let's say 3, and then we'll say 5 squared. Okay. So let's say that's the situation we're presented with. Well, you might be wondering, there is no index here. So what am I supposed to do with this? Because there's no index here, right? Well, the reality is that there actually is an invisible 2. When it comes to the square roots of stuff, there's an invisible 2 right there. So I think we could already see which prisoners are going to be able to get out of jail because this prisoner called 2 is showing that exponent right here that matches the index. Similarly, the prisoner called 5 is showing that exponent that matches the index as well. So therefore, who gets out of jail? Well, that would be the 2 and the 5. So we're going to multiply them on the outside of the prison cell. Who is stuck in the prison? Unfortunately, that 3 is stuck. All right, so I'd like to draw your attention to 2 things. Number one, when we jailbroke this prisoner, remember, only the base gets out, not 2 square, but 2 itself. There it is, right? It's almost like this 2 it's almost like this exponent is like a waiver for freedom, okay? And this prisoner, uh, or a ticket to freedom, and the prisoner gave the jail guard the ticket, and then the prisoner gets out of jail, and okay, there the prisoner is. Similarly, the 5 got out of jail, just 5 got out of jail. And the other thing I'd like to draw your attention to is the fact that these get multiplied. Okay, so let's actually do that. So we're going to have a 10 on the outside of the prison cell, and then we have radical 3. So those are very important skills that you will need moving forward. Now, unfortunately, there is sort of another thing that can happen that we need to pay attention to. And that is the fact that occasionally it's not going to be so straightforward. So, for example, let's say we have cube root, and this is 2 to the third, okay, fine. 5 to the fourth, though, and then we have maybe, yeah, we'll actually leave it like that. So imagine we had 2 to the third times 5 to the fourth, well, it's obvious that this blue 2 is going to get out of jail, so we could kind of do that. We could just put the 2 on the outside, and um, we would have this 5 to the fourth left over. However, unfortunately, we're not done, believe it or not, because anytime the exponent that hovers above a prisoner is more than the index, that means that some more can be done with that thing. Okay? So the reality is that 5 to the fourth could be, I'll just use black here. 5 to the fourth could be rewritten as 5 to the third times yet another 5 to the first power. Okay, now what am I doing here? I am splitting the base. Remember, I told you could split the base. Um, you got to make sure that the exponents add up to the original exponent, which is 4. But what I've done is I've, in a sense, extracted an exponent of 3 out of this situation. Okay, now seeing as how you can do that, that means that this blue 5 gets out of jail, not the other 5, but only the blue 5. So what are we left with on the outside? Well, we would have 2 times the blue 5, right? Times the cube root of just that 5 to the first power, which is just 5. And at that point, we can multiply the 2 and the 5 together. You would have 10 cube root of 5. Okay, so that's how you would simplify this scenario. Okay, so pretty tricky. Now, let's say we have another tricky situation let's say this is the fifth root right here, okay? And let's say we have 2 to the third, we have 3 to the seventh, okay? And then we have 5 to the 10th, okay? So things are getting kind of interesting right now. Well, first of all, this prisoner is stuck because the prisoner is showing an exponent that actually is less than the index. So this thing is definitely stuck. However, 3 to the seventh, 7 is certainly more than 5. So I think we can all agree that the 3 to the seventh could be rewritten as 3 to the fifth times 3 squared. Now, I'll just write the 5 raised to the 10th power right now. We're going to deal with that soon. I do want to just focus only on this 3 right there. So we already know that that 3 is going to get out of jail because that 3 is showing an exponent that matches the index. So let's actually get it over with. We're going to put that 3 on the outside of the prison cell. And then we have the 2 to the third left over. And then we have the 5 to the 10th. Now, you might be looking at this 10 and you might be thinking to yourself, well, okay, cool. The 10 is certainly more than 5, so maybe we could do something similar. Perhaps we can split the base. Well, you could, but it's not just that this 10 is more than 5. This is a slightly more unique situation in that not only is the 10 more than the index, but it's the case that this 10 is a multiple of 5. So whenever you have an exponent that's a multiple of the index, what that means is you can then rewrite that to force there to be the 5 on the outside, and what would be on the inside? It would be 5 squared, okay? Remember that previous rule that we covered that said that exponents can be split as well. This is 5 to the second raised to the fifth, and, that's just the reality of it. So then when we analyze, well, who is showing the jail guard an exponent that matches the 5 in the index? Well, it's this entire number right there. That's showing the exponent of 5 that matches the index, okay? So who gets out of jail? This entire thing gets out of jail. So therefore, what that would look like is we have the 3 kind of minding its own business. We have the 5 squared out of jail. Remember, it's not going to be to the fifth power because this is like the ticket to freedom. This blue parentheses handed this ticket over to the jail guard in exchange for his freedom. So then we have this fifth root shenanigans, and then we have the 2 to the third that's sort of left over underneath. Okay, now most teachers would want you to simplify that further. This is really 25, so there's going to be 3 times 25, aka 75, and that's going to be the fifth root of 2 to the third, which happens to be 8. So then you would be done with that one. All right, let's do one more example, an example that sort of combines everything. So we're going to do these square roots. So let's imagine we have 2 times 3 squared times 5 to the third times 7 to the 21st times 11 to the fourth. Okay, so what we're going to do is instead of doing these sort of intermittent jailbreaks, we're just going to mess with everything and then we're going to do a jailbreak in one shot. Okay, now the reality is that there is secretly a 2 in the index here. So on the first pass, the 2 that's here is just stuck. Who's going to get out of jail? Anytime I see something that gets out of jail, I'm going to make it blue. So this guy is going to get out of jail. This 5 to the third could be rewritten in such a way that we split the base. We could call that 5 to the second times 5 to the first. Oh, look, who else is going to get out of jail? That blue 5 is going to get out of jail. Looking at the 7 to the 21st power. Okay, Well, that's an interesting one. We're going to cross that bridge in a moment. Let's look at this 11 to the fourth, though. So the 11 to the fourth is going to be 11 squared squared, right? So who's going to get out of jail there? Well, it's going to be that 11 squared. Now, you might be wondering, why did I skip past this? Well, because this is a slightly uh, trickier situation, I would say, where we know that there's the 2 in the index, right? So what if we did a funny thing? What if we did a thing where we did 7 to the 20th times an extra 7 to the first? That's nothing more than splitting the base, and 20 plus 1 is equal to 21. Well, you might be wondering, why did I do that? That's ridiculous. Well, the reason I did that is because that's a number that is a multiple of 2. So what that means is on the next pass, I could say 2 times 3 squared times 5 squared times an extra 5 to the first power times, instead of writing 7 to the 20th, I can write 7 to the 10th power raised to the second power, right? Because you can split that exponent to, in a sense, force it to have a 2 on the outside. And that's going to be times 7. And then we have times 11 squared squared. So looking at who gets out of jail, this 3 gets out of jail, this 5 gets out of jail, this entire number gets out of jail, and this entire number gets out of jail. So therefore, on the outside of the prison cell, we would have the 3 times the 5 times the 7 to the 10th, which is some huge number, times the 11 squared, okay? Who's left over in the jail cell? Well, that would be the 2 times the 5 times the 7. Now, all of these would multiply to something quite large. This is going to multiply to 70, so you can put a 70 underneath. So for my student watching this, I know it might be confusing. That was a crazy one that I just did. I don't think you're going to have to do anything like that. But nonetheless, I did want to demonstrate the various principles involved, because if you could at least have a glimmer of understanding of what just took place here, then you're going to have a really good shot at the problems on the worksheet. All right, let's move forward. Okay, moving forward to this worksheet right here. So a couple of things to keep in mind, a couple more concepts to keep in mind. It is the case that anytime you have a fractional exponent, you could kind of think of tilting the fraction to the right. Now that 1 ends up here and the 2 ends up there. Okay, so that's something to consider. Similarly, if you were to tilt this fraction of 1/3 to the right, well, the 1 would end up here and the 3 would end up right there. So when they say nth root, that's just their way of like saying this would happen under all circumstances. It's generalizing it, okay? So you could tilt the 1 over n and the n ends up here. And then maybe the 1 would be right there. Now, the real takeaway is that whatever the denominator is, that ends up being the index. In my opinion, for this particular worksheet, that's the primary takeaway when it comes to converting fractional exponents into radicals, all right? At this point, I think we're ready to do it. So 14 to the 1/2, well, what would happen if we tilted that fraction over? That clearly would be 14 underneath a radical with a little 2 in there, also known as just the square root of 14. It's possible the teacher wants you to know that, yes, there is a 2 there, but you actually don't have to write it because it's customary to just leave it as an invisible 2. The trick of this is to recognize that only the x is being raised to the 1/2 power, so therefore the 5 is just minding its own business on the outside, and then we would have radical x, so that's that one. In this case, we have 12 underneath the radical. It's the square root of 12. Now, let's do a prime factorization on 12. 12 gets, if we add the list of prime numbers, 2, 3, 5, 7, 11. 2 times 6, 2 times 3. So therefore, 12 could be rewritten as 2 times 2 times 3, also known as 2 squared, times 3. Who gets out of jail? Well, this blue 2 gets out of jail. So therefore, that could be simplified as 2 radical 3. Okay, so we're sort of tying all of the concepts together right now. The variable that has a fractional exponent is b. A does not have an exponent, 19 does not have an exponent, so therefore 19 and a are minding their own business on the outside of the radical symbol, and then you have that b right there, so that's that one. Okay, so we already figured out that 12 is really 2 squared times 3, so I kind of feel like we could just rewrite that as 2 squared times 3 times n. Who gets out of jail? Well, that 2 gets out of jail, so that ends up being 2 radical 3n at the end of the day. Once again, the prison cell analogy at work. 18, let's do a prime factorization. 2 times 9, and then 3 times 3. Those are prime numbers. How do I know? 2, 3, 5, 7, 11, right? We started with 2. We asked ourselves, does 2 go into 18? Yes, it does. So we did 2 times 9. Then we focused on 9. Does 2 go into 9? No, it does not. So then we move to the next number in the list. Does 3 go into 9? Yes, so it's 3 times 3. And that's all prime numbers. So therefore, 18 could be rewritten as 2 times 3 times 3, also known as 2 times 3 squared, times b. Who gets out of jail? Well, that 3 gets out of jail. Look at that. So the 3 is on the outside, and you have 2b left over. All right, prime factorization. Once again, let's get that. We'll just get the list over here. 2, 3, 5, 7, 11, right? Okay, so looking at 343, does 2 go into 343? No, it does not. Does 3 go into 43? No, I don't think so. Does 5 go into 343? No. Does 7 go into 343? Maybe. Maybe. I think so. Oh man, this one's crazy, right? So 7 times 4 is 28. 14 minus 63. Yeah, so yeah, so 3 goes in 7 rather goes into 343. It looks like 47 times. So what that means is that we could, if we wanted to, rewrite this as the cube root of 7 times 47, because the 47 is actually prime. As far as I could tell, yeah, there's nothing that goes into 47. So the reality is we're actually stuck with this situation. Cube root of 343 is literally just the cube root of 343. We cannot simplify that any further because these are prime numbers, so nobody gets out of jail, in other words. So that's that one. That's kind of a weird one. Okay, this one right here, if we were to do the prime factorization tree, 1024, certainly 2 goes into that. I believe that would be 512. 2 certainly goes into that. That's going to be 250 plus 6, also known as 256. 2 goes into that. That's going to be 1, 2, 8, I believe. And then 2 goes into that. That's going to be 64. 2 goes into that. That's going to be 32. I already kind of see where this is going. 16, 2, 8, 2, 4, and finally 2, 2. So pretty crazy, right? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2. So literally, it's going to be the fifth root of 2 to the 10th. Now, let's analyze this situation. That's really the fifth root of 2 squared to the 5th. So who gets out of jail? This blue guy gets out of jail. In fact, that entire blue guy gets out of jail. So 2 squared is just free, and that's just 4. Okay, so it turns out the fifth root of 1024 is 4. We got that, of course, by applying the prime factorization tree to 1024. That resulted in 2 to the 10th power, and then we could perform the previously mentioned strategy to this to recognize that it's the 2 squared that gets out of jail. Okay, so looking at problem number 12. So in this case, that is most definitely the cube root of 512. Let's perform a prime factorization tree on that. 5, 1, 2. So if we were to perform the prime factorization 3 and 512, acknowledging these prime numbers. We're looking at 2 times 256. Again, I feel like we were here already. That's going to be 2 times 128, which is 2 times 64, which is 2 times 32, which is 2 times 16, 2 times 8, 2 times 4, 2 times 2. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 total twos there. So therefore, cube root of 512 could be rewritten as the cube root of 2 to the ninth. Now we know the trick to perform with this one. 2 to the ninth could be rewritten as 2/3 raised to the third, in a sense forcing that exponent of 3 on the outside because that matches this. So who gets out of jail in that case? Well, this entire parentheses gets out of jail, so that would be 2 to the third just roaming free outside of the prison cell, and that happens to be 8. Okay, so that's that one. Okay, this one right here looks not very fun. Okay, 2,401. I'm not so sure what the prime factors would be for that because it's not divisible by 2. I can see it's not divisible by 3 because the digits 2, 4, 0, and 1 do not add up to a multiple of 3. So it's possible that that right there is not divisible by anything. But let's take a look. Is it divisible by 3? No. Is it divisible by 5? No. Is it divisible by 7? Well, actually, I think it turns out that it is. So 2401 is divisible by 7 because 7 times 343 happens to be 2,401. 343 is also divisible by 7. That's going to be 49. And then, of course, that's 7 and 7. So it turns out that there are 1, 2, 3, 4 sevens. So therefore, 2,401 could be rewritten as 7 to the fourth. Who gets out of jail? This blue 7 gets out of jail. So therefore, we're looking at just a 7. Okay. Let's see. 6 to the 64 right here to the sixth root of 64. So 64 is a result of 2 times 32. And through our sort of previous process here, we saw that 32 is really just 5 2's getting multiplied together. 2 times 2 times 2 times 2 times 2. So 2 to the fifth equals 32. So therefore, what I'm going to do right here is I'm going to sort of do a little shortcut where I just have 5 2's emitting out of that. Okay, I'm going to get a little fancy there. All right. So the reality is that 64 is secretly 2 to the sixth power. So who gets out of jail? This blue 2 gets out of jail. So that's the answer to that one. Looking at 243 to the 1/5. Well, I feel like did we already do 243? No, unfortunately we did not. So 243 to the 1/5 power. Well, let's see. 243, not divisible by 2. Is it divisible by 3? Yes, it is, because 2 plus 4 is 6, and 6 plus 3 is 9, and 9 is divisible by 3. So we're looking at 81 there. 81 is divisible by 3. 3 times 27, which happens to be divisible by 3. 3 times 9, which happens to be divisible by 3. 3 times 3. So we have 1, 2, 3, 4, 5 3's. So we have the fifth root of 3 to the fifth. So who gets out of jail? That blue 3 gets out of jail. So therefore, this ends up literally just becoming 3. Looking at this one, 1, 3, 3, 1. Is that divisible by 2? No. Is that divisible by 3? I don't know. We have 1 plus 3 is 4, plus 3 is 7, plus 1 is 8. So that doesn't really help us. Let's see. Is 1331 divisible by 5? No, it is not. It might be divisible by 7. It is not, unfortunately. So if you were to investigate each of these all the way up the line after 7, you would actually see that 11 does indeed go into 1331, and that would be 11 times 121. Now 121 is 11 times 11. So it's the case that the cube root of 1331 is the same as saying the cube root of 11 cubed, and who gets out of jail with that blue? 11 gets out of jail, therefore the answer to that is just 11. So these are all very straightforward. Looking at 6, 5, 6, 1, let's see, is it divisible by 2? No. Is it divisible by 3? I don't know. 6 plus 5 is 11, plus 6 is 17, plus 1 is 18. That is divisible by 3, so therefore 6,561 is divisible by 3. 3 goes in, looks like it would be 2. 1, let's see. Trying to do this without having to bust out long division. 2,187. Okay. Now, is that divisible by 3? Let's see. 2 plus 1 is 3, plus 8 is 11, plus 7. Yeah, so that's divisible by 3 as well. And that's going to be 7, 2, 9. Is that divisible by 3? 7 plus 2 is 9. Yeah, so that's divisible by 3 as well. So that's going to be 2, 4, 3. I feel like we already just dealt with the 243 now. Yeah, we dealt with the 243 right here. 243 turned out to be 3 to the 5th. So let's just force this to have 5 3's coming out of it. All right. So how many total 3's we have? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 3's. Therefore, it's really going to be the 4th root of 3 to the 8th. And let's go ahead and rewrite that 3 to the 8th to force it to have that exponent of 4 on the outside, and therefore it would be 3 squared on the inside. Who gets out of jail? Well, this guy gets out of jail. So 3 squared roams free, and then 3 squared is, of course, 9. Okay, so that's that. Looking at 409. 409. Let's see. Does 2 go into that? No. Does 3 go into it? 4 plus 9 is 13, and 13 is not divisible by 3. So upon investigation, you would quickly see that 409, or not quickly, you would see eventually that 409 is not divisible by any of those prime numbers. So we are actually sort of stuck with the 4th root of 409 because that has no factors other than 1 and 409, which means that 409 is itself prime, and therefore we cannot break that down any further, and therefore we are stuck with this. Okay, so looking at this page right here, let's see, write each expression in radical form or write the radical in exponential form. So in a way, we're going backwards. This just turns into 13 to the 1/2. This turns into 37 to the 1/2. This turns into 17x, the whole thing, to the 1/2. That's important. We could also say that that's equal to 17 to the 1/2 times x to the 1/2. But for my student watching this, double check to see which answer the teacher prefers. All right. Bottom line is it is the entire 17x that's being raised to the 1/2 because it is the entire 17x that's under the radical. Similarly, this would be 7ab square rooted if we were to tilt that fraction over and turn that into a radical. Only the z is being raised to the 1/2, so this is going to be 21 on the outside with a z on the inside. Only the AB is being raised to the 1/2, so that's going to be 13 on the outside, AB on the inside of the radical. Simplifying this, well, it is the case that that's 1 to the 1/4 over 81 to the 1/4. You could sort of apply that exponent here and down there. And 1 to the 1/4 is really just the fourth root of 1, so I'll write that, that's fine. And then we have the fourth root of 81, and fourth root of 1 is just 1, and the fourth root of 81 is just going to be 3. You can always verify that by doing the prime factorization with that, and you would quickly see that there's 4 of these 3s, so 81 is 3 to the 4th, so who gets out of jail? Just 3. Okay, so that's that one. 1024. We had actually dealt with that on the previous page, so this is a bit of a repeat. You may recall that after performing the prime factorization tree, that was 2 to the 10th power, and we acknowledged that we could therefore rewrite it as forcing that exponent of 5 on the outside, and therefore 2 to the 2nd on the inside. So who gets out of jail? The 2 to the 2nd, also known as 4. Okay, 512, I believe we did that on the last slide as well. It turned out that, well, first of all, let's rewrite it as the cube root of 512. Now, through the prime factorization tree in the previous slide, it was the case that 512, after doing the prime factorization tree, was 2 to the 9th. Now, 2 to the 9th could be rewritten as a number that has a 3 on the outside, and therefore it would be 2 to the 3rd on the inside. So who gets out of jail? The 2 to the 3rd right here gets out of jail. So therefore we're looking at 2 to the 3rd, which is 8. Okay, so that's that one. Okay, so the exponent of 1/5 would get applied to the top and the bottom. We're looking at the 5th root, therefore, of 32. We're looking at the 5th root, therefore, of 1024. It was the case from the previous slide that 32, you may recall, is 2 to the 5th. Okay, we did talk about that briefly, and then we just finished saying that 1024 is 2 to the 10th. So it's the case that the 2 on the top is going to get out of jail, so we can get that over with. We have a 2 on the top. Down below, it's the case that we have a 2 squared being raised to the 5th, so who gets out of jail? Just the 2 squared gets out of jail. So therefore we have 2 over 2 squared, which is 4, and therefore it's 1/2. Okay, 1296. So I do not believe we did the prime factorization tree for 1296. It's certainly divisible by 2. 2 times 648 would give us 1296. 648 is divisible by 2. 2 times 324. 324 is divisible by 2 as well. That's going to be 162, which is divisible by 2, which is going to be 81. And we already know that 81 is a result of 3 times 3 times 3 times 3. So we're looking at 4 3s and 4 2s. So we have 2 to the 4th times 3 to the 4th. So who gets out of jail? Literally both of these prisoners get out of jail. So we have 2 times 3, which is just 6. Okay. Problem number 12. We have dealt with a 3125, did we? Yeah, actually, I don't think we did. Either way, it's going to be the 5th root of that. So 3125. Prime factorization tree, definitely divisible by 5, but is it divisible by 3? Let's see, 4. No, it's not. So it's divisible by 5. 5 times, let's see, 600 and something. Let's see, 3125 divided by 5 would be 625. Okay, so that's divisible by 5. I believe 125, and that's divisible by 5. 5 times 25, and then, of course, 25 is a result of 5 times 5. So 3125 is 1, 2, 3, 4, 5. So that's 5 to the 5th power. And it turns out that this blue 5 gets out of jail. So therefore, 5 is there. Okay, looking at problem number 13, these equations challenge you to uh, ensure that the base that's represented on the left side of the equation matches the base that's represented on the right side of the equation. Now, it's probably the case that 729 could be rewritten as a base of 3. So if I was to divide 729 by 3, it would be 3 times, I guess it would be 263. And if I was to divide 263 by 3, that would be 81, I believe. And if I was to divide that by 3, that's 27. And then we have 3 times 9 and 3 times 3. So it's the case that 729 is a result of 1, 2, 3, 4, 5, 6 threes getting multiplied together. So 3 to the x actually equals 3 to the 6th. And therefore, you can sort of use logic and say that, okay, well, clearly these exponents have to be the same. So you could write that underneath. So that's basically how you do these equations. You just make sure that the base on the left matches the base on the right. Okay, so when it comes to problem number 14, it is true that 4 to the x power could be rewritten as 2 squared to the x power, which could be rewritten as 2 to the 2x. Now, I would actually do that. I would whittle each of these numbers down to the most sort of reduced base possible. 4096, let's see, prime factorization tree. We have 2, 2, 0, 4, 8. That's 2 times this. And I believe we tackled that on the previous slide. If we were to break up 1024, that would be 2 to the 10th power. So I'm just going to write 2 to the 10th power right there. So the reality is that this could be rewritten as 2 to the 12th because we have these two plus the extra 10 twos right there. So therefore 2x equals 12, divided both sides by 2, x equals 6. Okay, so it's that one. Problem number 15. Okay, the question is, what's 15625 if we were to do a prime factorization tree? So I'm starting to see that this approach, although common, is kind of tedious. Okay, I think we all know there's a strong possibility that this number has a base of 5. It's going to be 5 to the something power. So what I'm going to do is I'm going to use my calculator. I'm going to investigate, 5 to the second, 5 to the third, 5 to the fourth. And I'm going to keep going until the calculator tells me that it becomes 15,625. So I'm going to throw in 5 to the sixth just to kind of mess with it. Oh, so I'm actually lucky. I threw in 5 to the 6th power and it immediately gave me 15,625. So we know that 5 to the x equals 5 to the 6th, therefore x equals 6. All right, so that's, even though I guarantee the teacher does sort of like the prime factorization approach, but these numbers are starting to get like really big and I don't want to do that. Okay. I think there's a strong possibility that this probably has a base of 6, right? Because this is like 6 to the x plus 3 on the left. So the question is, this is 6 to the what power? Well, I'm going to use my calculator. I'm going to try 6 to the 5th power and see what happens there. Oh, look, I am lucky. I'm very lucky. 6 to the 5th power is immediately showing 7,000 776. So this is 6 to the 5th power. So therefore we can say that x plus 3 equals 5, and therefore we could say that x equals 2. Amazing. Probably the case that 2187 has a base of 3. I'm going to use this calculator shortcut. I'm going to say, let's see, 3 to the 5th. What is that? That's 243. What about 3 to the 6th? What's that? That's 729. What about 3 to the 7th? 3 to the 7th is 2,187. So therefore, we could sort of replace that question mark with a 7, and therefore x minus 3 equals 7. Adding 3 to both sides gives us x equals 10, and we're done with that one. Okay, so 2 squared raised to the 3x plus 4. Now, once again, anytime you have a power raised to another power, you can multiply these. So we do want to be careful when you multiply the exponents. It's going to be 2 times this entire quantity, which means it's going to be 2 sort of distributed to that and to that. So therefore, we're looking at 2 to the 6x plus 8, and that's going to equal 2 to the something, right? We're going to use our calculator here. I'm going to go with 2 to the 10th, first of all. That's 1,024. 2 to the 11th is 2,048. 2 to the 12th is 4096. 2 to the 13th is 8192. 2 to the 14th is 16384. So it turns out that 2 to the 14th in my calculator gives me 16,384. So I'm going to replace the question mark with a 14. And therefore, we can set up a new equation that says 6x plus 8 equals 14. After going through the motions, you would see that x equals 1. Okay, so that's that one. Looking at problem number 19, the flow of water F in cubic feet per second over a wire? I don't even know. A small overflow. Okay, so that's a word for a small overflow dam. Can be represented by F equals blah, blah. Cool. Where h is the height of the water in feet above the crest of the dam. Find the height of the water if the flow of the water is 10.08 cubic feet per second. Okay, fine. So in other words, replace F with that because that is the flow, right? And sort of write the equation, and they want to know what is the height going to be. All right. Pretty crazy. First of all, we have a fractional exponent. So what we're going to do is we're going to tilt that fraction, okay, over, and then that's going to become 1.26 radical with a little 2 here, and then we got a little h here, and then we could put the 3 here. Now, we don't have as much practice putting the 3 here. The numerator goes here. It could also go somewhere else, but let's just keep it simple. It goes here, okay? And that's what's happening. So what do we do from here? Well, I feel like we could divide both sides by 1.26, but let's look at this. And I'm going to rewrite it so it just looks a little nicer. This is where we are right now. Square root of h cubed. I feel like we could definitely divide by 1.26. Okay, that would cancel that. And it is the case that 10.08 divided by 1.26 is 8. Okay, so we have 8 equals the square root of h cubed. So this is a strategy that we have yet to cover, but it is the case that we're trying to solve for this red h. Now, I think people would agree that this sort of radical square root action is in the way. So what we're going to do, in the way of isolating the red h, we want to ultimately get this red h all by itself on the right-hand side, which means we got to get rid of all this stuff. We're going to have to get rid of that exponent of 3 as well, but we got to sort of attack this from the outside in. So let's first get rid of that square root symbol. And the opposite of square rooting something is to square something. So we can actually square both sides right now. okay? So h squared is 64, and then the squaring action of the square root symbol actually cancels the square root symbol out, and then we have h cubed. Okay, now we're almost there. I mean, we almost have this h by itself, but the problem is it's being raised to the third power. So how do you get rid of that exponent of 3? Well, you have to do the opposite of cubing something, which is to take the cube root of something. So we're going to take the cube root of this side, but of course you have to do it to the other side as well. So when you take the cube root of the right side, it cancels that exponent of 3, leaving us with just an h left over. But then the question is, what's the cube root of 64? I don't know, prime factorization, 2 times 32. And this is, I know 5 2's from previous problems. So 64 is secretly 2 to the 6th. And using our previously mentioned strategy, 2 to the 6 is secretly something to the third power, namely 2 squared to the third power. Who gets out of jail? This blue parentheses gets out of jail. So therefore, we could say that h is equal to 2 squared, which, by the way, is, of course, 4. So that's the answer to that one. Hopefully this was helpful. Quite dense information. I did move through it pretty quickly, but if you noticed any mistakes, please let me know in the comments. And hopefully this was helpful, and I will talk to you all later. Bye.